Hey everyone, in this video we will go over motion constraints. When we compare motion constraints and assembly constraints define the position of components in an assembly, where a motion constraint defines motion ratios between assembly components, or how components move relative to one another. Let's take a look at motion constraints. When doing this, we need to define the type of motion, so rotation or translation. We then need to define ratios, so in the case of gears, we will define their gear ratios. Finally, just like assembly constraints, we can give limits to the motion constraints. I have this simple gear train, and we will use motion constraints to define how these gears move in relation to one another. As you can see, currently the gears and the rods are rotating independently of one another, so we first need to constrain the movement of the gears and the rods together by mating their origin planes. To do this, let's open the drop-down folder of one instance of the gears and turn on the visibility of the desired plane. This should turn on the visibility for all instances. We can do the same for the rods. Now we can go ahead and mate the planes of the gears and their respective rods together. Hit the constrain button and use the mate constraint to constrain the movement of the rod and the gear together. You can see now that the rods and the gears rotate as one. One thing to take note of is the solid green cube, which indicates that the component is constrained to an unconstrained component. This is because rotation is still a degree of freedom. We now need to place motion constraints on the gears so that we can define how they move with respect to one another. First, to clean up our model, we'll turn off the visibility of the planes. Go ahead and hit constrain, and we will now go into the motion tab. Notice here we have the option of rotation or rotation translation. We are solely working with rotation here, so we will select that option. We also have options of forward, which means the gears are rotating in the same direction, which we can use for compound gears, or reverse, which means the gears are rotating in the opposite direction, and we can use this for meshing gears. You can input the speed ratio of your gears under the ratio dialog box. Since the gears in our example are all the same size, our speed ratio will be 1. Note that Inventor takes the ratio of the first selection to the second selection. So we need to select the output gear, then the input gear, if we want to specify the ratio using diameters. If we want to specify the ratio using speed, we can then select the input gear, then the output gear. Once that is all specified, click Apply. For the next set of gears, we are working with compound gears. Let's use the rotation forward constraint on the compound gears so that they will rotate in the same direction. Once again, the gear ratio is 1, and we will select the output gear first, then the input gear, then hit Apply. Go ahead and place the last motion constraint on the final gear pair, and we now have a constrained gear train. A useful tool that we can use is the degree of freedom analysis. In the Assemble tab, under the Productivity section of the ribbon, open the Create Substitutes dropdown. At the bottom of the list, you will find a degree of freedom analysis. Click on that. Here you will find a table listing the degrees of freedom for each component. You can see that the gears 1, 2, and 3 are still free to rotate. At the bottom, you can check off the Animate Freedom box, then select a component in the table, and you will see that the component is animated, displaying the movement along any remaining degrees of freedom. Notice that gear 4 has no degrees of freedom, and that's because its rotation is completely defined by the compound gear and the meshing gear. This tool is a great tool to open up when you want to ensure that you have placed all the necessary constraints on your components. This concludes our video on motion constraints.